All right, ladies and gentlemen, this is going to be not a review video this time, but an explain video all about orbital hybridization. Because it's something that I'm going to bring up now and again in class, but you really truly don't need to know that much about it. It's just helpful to understand what it is. So first of all, what even is orbital hybridization? So remember all of these SPDF1s, the S orbital spaces were spherical, the P orbital spaces were dumbbell shaped, the D orbital spaces were cloverleaf shaped, and the F orbital spaces were just straight up weird. They had a lot of variability. Well, basically, orbital hybridization happens when these orbital spaces smash themselves together and they hybridize to make new shapes. And they do this because sometimes hybridizing together is more stable than remaining separate. All right, so there's a few possibilities of hybridization. You could have sp3 hybridization, which involves a single s orbital space and 3 p orbital spaces smashing themselves together. So this could be the 2s orbital space with the 2p orbital spaces, or it could be the 3s orbital space with the 3p orbital spaces, or 4s with 4p, so on and so forth. You could have sp2 hybridization, which involves one s orbital space hybridizing with 2 of the 3 p orbital spaces. And again, this could be the 2s with 2 of the 2p's, or the 3s with 2 of the 3p's, so on and so forth. You could have an sp hybridization pattern where one s orbital space and 1 of the 3 p orbital spaces hybridize together, leaving the other 2 p orbital spaces out. You could have an sp3d hybridization pattern where you have one s orbital space, 3 p orbital spaces, and a d orbital space all hybridizing together. And you could also have an sp3d2 pattern wherein you have one s orbital space, 3 p orbital spaces, and 2 d orbital spaces all smashing together. And yes, obviously, because this is chemistry, there are more options than just that, but those are the ones you see on your Vesper sheet, and those are the ones you're going to deal with in this class. So in terms of giving you a visual representation of what I mean by hybridizing, we have to go back and look at an example that you already are familiar with. So if we look at carbon's normal electron configuration, it is 1s2, 2s2, and 2p2. So what that means is that in its core shell here, closest to the nucleus, we have 2 electrons hanging out in a spherical orbital space really close to the nucleus. And in its valence shell, we have 2 of those electrons hanging out in a spherical orbital space and 2 of them hanging out in a dumbbell-shaped kind of space over there. All right, but again, this is their normal configuration. Without hybridization, if you pay attention to the orbital diagram or the arrow diagrams here, it looks like carbon could only bond twice. And the reason it looks like that is because you are only seeing 2 unpaired electrons in its normal configuration, right? But we know that carbon can bond up to 4 times, and it can do that because those orbital spaces, this one and these ones, can hybridize, and they do. So let's say that carbon was going to hybridize in an sp3 pattern, all right? What that means is that the 2s and 2p orbital spaces are going to smash themselves together. And what that does is it produces a total of 4 unpaired electrons instead of just 2. So basically, this little downspin electron is going to migrate over to this area, and all of those little orbital spaces end up smushing together, and that sphere and that cloverleaf end up looking more like something like this that you're seeing over here. All right, so we're seeing 1 space, 2 spaces, 3 spaces, and I know it's a little difficult to see, but right back there's one orbital space that's kind of behind. And those electrons are going to occupy all 4 of those spaces. There's going to be 1 electron here, 1 here, 1 here, and 1 in that little backwards facing one. And so we would redraw the orbital diagram like this with 4 unpaired electrons, and each of those unpaired electrons could then theoretically form a bond with something else. And we see this happen all the time, right? CH4, we know that carbon is bonded to each of those 4 hydrogens, and this is why carbon is able to do that. Let's say that carbon, instead of hybridizing in an sp3 pattern, hybridizes in an sp2 pattern instead. Well, similar, we still see that little downspin electron coming over here and becoming unpaired. However, only 3 of those 4 potential orbital spaces end up smashing themselves together. So this orbital space and these 2 will end up smashing together to form this 2sp2 space, and then that last electron over in this space just remains unhybridized. And you're seeing that over in this picture, so we can see again the hybridized spaces here, here, and here, but we're seeing that leftover p orbital here in the gray, okay? So those electrons, the hybridized ones, one's going to be in this space, one in this space, one in this space, and then that leftover electron is going to remain in that p orbital space right there. Last but not least, that carbon could sp hybridize. Again, we're going to see that exact same promotion. That little downspin electron is going to hop directly over here to become unpaired, but only 2 of the orbital spaces are going to smash themselves together, creating the 2sp, it should be 2sp, and then the leftover 2 orbital spaces are just going to remain unhybridized. And so over here in this picture, we're seeing the hybridized space here and here, and those 2 electrons are going to occupy that space, and then our leftover 2 from here are going to occupy one of these and one of those spaces. All right. And again, I know that you don't really have a frame of reference for what that means or why it's important. But again, the good news is that you don't really have to understand why that electron jumping happens, why the hybridization happens at all. That's kind of beyond the scope of this class. I just wanted to provide you an explanation should you want one. What you do need to be able to do is just recognize a hybridization pattern given a formula or a Lewis structure or both, right? So let's look at CH4, right? The example I used before. If you look at the Lewis structure in CH4, we can see that there are 4 things on that carbon atom. And I say things, not atoms, because electron pairs are going to count as a thing as well. So as soon as you recognize that there's 4 things, 1, 2, 3, 4, on that carbon atom, all you need to do is find a hybridization pattern that has 4 things in it, right? So if I look at my options down here, S and P are 2 things. So that one is out. S and 2 P's, that's a total of 3 things. So that one is out. An S and 3 P's, that's a total of 4 things. So sp3 is our hybridization pattern, right? So this one would be sp3 hybridized. And I'm going to abbreviate that just for the sake of space. Moving on to example number 2. We can see, based on the Lewis structure for CH2O, that there are 1, 2, 3 things on that carbon. So we need to find a hybridization pattern that has 3 things. Once again, S and P, that's 2 things. But S and 2 P's, that's 3. So this one would be sp2 hybridized. All right. Last example, we have H2O. We can see in H2O that there are 1, 2, 3, 4 things on that oxygen. Not 2. There's 2 atoms and 2 electron pairs, so that's a total of 4 things. So we would want sp3 because an S and 3 P's is a total of 4 things, making this oxygen atom sp3 hybridized. So again, this is what you need to be able to do on the AP test. You need to be able to look at a formula, look at a Lewis structure, and predict your hybridization pattern. That's it. You don't need to know any of the stuff up here. You don't need to understand what the orbitals look like. You don't need to understand how the electron promotion happens. None of that. You just need to be able to look at a formula and select the correct hybridization pattern. If you're struggling with that, I am happy to go over some examples with you in class, but I hope this was helpful.